Hello everybody. Now watching to computer graphics unit 2. First topic, raster scan systems video controller. First one, raster scan systems. It is addition to the central processing unit a special purpose processor called the video controller or display controller. It is used to control the operation of the display device. It is a simple raster system. Next topic, video controller. The frame buffer can be anywhere in the system memory and the video controller accesses the frame buffer to refresh the screen. In addition to the video controller, more sophisticated for raster systems. A fixed area of the system memory is reserved for the frame buffer and the video controller is given direct access to the frame buffer memory. The frame buffer locations and the corresponding screen positions are referenced in Cartesian coordinates. The next, this slide basic refresh operation of the video controller. The screen surface is then represented as the first quadrant of a two-dimensional system, with positive x values increasing to the right and positive y values increasing from bottom to top. Scan lines are then labeled from y maximum at the top of the screen to 0 at the bottom. Along each scan line, screen pixel positions are labeled from 0 to x maximum. Two registers are used to store the coordinates of the screen pixels. Initially, the x register is set to 0 and the y register is set to y maximum. The value stored in the frame buffer for this pixel position is then retrieved and used to set the intensity of the CRT beam. Then the X register is incremented by 1 and the process repeated from the next pixel on the top scan line. This procedure is repeated for each pixel along the scan line. After the last pixel on the top scan line has been processed, the X register is reset to 0 and the Y register is decremented by 1. The screen must be refreshed at the rate of 60 frames per second. The cycle time is too slow. To speed up pixel processing, video controllers can retrieve multiple pixel values from the refresh buffer on each pass. The multiple pixel intensities are then stored in a separate register and used to control the CRT beam intensity for a group of adjacent pixels. Next, raster scan display processor. A raster system containing a separate display processor, sometimes referred to as a graphics controller or a display coprocessor. The purpose of the display processor is to free the CPU from the graphic source. In addition to the system memory, a separate display processor memory area can also be provided. A major task of the display processor is digitizing a picture definition given in an application program into a set of pixel intensity values for storage in the frame buffer. The digitization process is called scan conversions. Graphics commands specifying straight lines and other geometric objects are scan converted into a set of discrete intensity points. Scan converting a straight line segment, for example, means that we have to locate the pixel positions closest to the line path and store the intensity for each position in the frame buffer. Similar methods are used for scan converting curved lines and polygon outlines. The next topic, random scan systems video controller. A simple random scan system and application program is input and stored in the system memory along with a graphics packages. Graphics commands in the application program are translated by the graphics package into a display file stored in the system memory. This display file is then accessed by the display processor to refresh the screen. The display processor cycles through each command in the display file program once during every refresh cycle. Sometimes the display processor in a random scan system is referred to as a display processing unit or a graphics controller. A graphics patterns are drawn on a random scan system by directing the electron beam along the component lines of the picture. Lines are defined by the values for the coordinate endpoints, and these input coordinate values are converted to X and Y deflection voltages. A skin is then drawn one line at a time by positioning the beam to fill in the line between specified endpoints. The next topic, line drawing algorithms. The Cartesian slope intercept equation for a straight line is y equal m into x plus b, equation 1, with m representing the slope of the line and b as the y-intercept. Given that the two endpoints of a line segment are specified at positions x1, y1 and x2, y2. Determine values for the slope m and y intercept b with the following calculations. M equal y2 minus y1 divided by x2 minus x1. It is equation 2. And then b equal y1 minus m into x1. It is equation 3. Algorithms for displaying straight lines are based on the calculation given in equation 2 and 3. For any given x interval delta x along a line, we can compute the corresponding y interval x delta y from equation 2 as delta y equal m into delta x. It is equation 4. Similarly, we can obtain the x interval delta x corresponding to a specified delta y as delta x equal delta y divided by m. It is equation 5. These equations form the basis for determining deflection voltage voltages in analog devices. Equation 4 and 5, delta y as calculated from slopes have magnitudes set proportional to a small vertical deflection voltage with a corresponding horizontal deflection voltage set proportional to delta x calculated lines with m equal 1, delta x equal delta y, and the horizontal and vertical deflection voltages are equal. In each case, a smooth line with slope m is generated between the specified endpoints. On raster systems, lines are plotted with pixels, and step sizes in the horizontal and vertical directions are constrained by pixel separations. The next topic, DDA algorithm. DDA means Digital Differential Analyzer. It is a scan conversion line algorithm based on calculating either delta y or delta x using equation 4 or 5. The line at unit intervals in one coordinate and determine corresponding integer values nearest to the line path for the other coordinate. Consider first line with positive slope. The slope is less than or equal to 1. Sample at unit x intervals delta x equal 1 and compute each successive y value as y subscript k plus 1 equal y subscript of k plus m. It is equation 6. Subscript k takes integer values starting from 1 for the first point and increases by 1 until the final endpoint is reached. Since m can be any real number between 0 and 1, the calculated y values must be rounded to the nearest integer. For lines with a positive slope greater than 1, we reverse the roles of x and y. That is, sample at unit y intervals delta y equal 1 and calculate each succeeding x values as x subscript k plus 1 equal x subscript k plus 1 by m. It is equation 7. Equations 6 and 7 are based on the assumption that lines are to be processed from the left endpoint to the right endpoint. This processing is reversed so that the starting endpoint is at the right. Then either have delta x equal minus 1 and y subscript k plus 1 equal y subscript k minus m. It is equation 8. Or have delta y equal minus 1 with x subscript k plus 1 equal x subscript k minus 1 by m. It is equation 9. Equation 6 through 9 can also be used to calculate pixel position along a line with negative slope. If the absolute value of the slope is less than 1 and the start endpoint is at the left, set delta x equal to 1 and calculate y values with equation 6. The start endpoint is at the right. Set delta x equal minus 1 and obtain y positions from equation 8. Similarly, the absolute values of a negative slope is greater than 1. Use delta y equal minus 1 and equation 9 use delta y equal 1 and equation 7. This algorithm is summarized in the following procedures, which accept as input the two endpoint pixel positions, one horizontal and second vertical. Difference between the endpoints positions are assigned to parameters. Thank you everybody watching this video. Thank you.